Welcome to Tutorial 3 for Embedded Development with the Zynq7000. And with the Zybo board, in this video we'll be creating custom IP that will generate an interrupt. And this interrupt will go into the Zynq7000 interrupt port, and you'll be able to handle this interrupt in software. So we'll be going over writing the drivers in C as well as generating the custom IP. So let's go ahead and get started. So the first thing we're going to do is create a new project. This shouldn't be too hard. If you've done this before, you should be pretty familiar with how to use Zynq's Vivado and SDK by the time you get to this tutorial. And maybe you've encountered some of the same issues I have when trying to create your own custom IP with an interrupt that will generate an interrupt to the Zynq processing system from the PL, and which you're also going to be able to handle in your software in the program code. In this tutorial, we're going to be covering how to create your own custom IP with an AXI interrupt that interrupts the Zynq processor, and how to write the drivers for it. So go ahead and just create a new project. I'm using Vivado 2017.4. The process shouldn't be that different if you're using other versions of Vivado. So just go ahead and create a project directory as well, and click Next. Just keep the just create a blank RTL project. We're not going to be importing any code. So there's no importing going on in HDL. So keep these settings sort of default the way they are. Click Next. Next you want to click on Board and import Zybo. Now if you've never done this before, you may not have a board support package for a Zybo board. There's a way to import boards. I'm not covering that in this video. If you have a question, ask in the comments. I can point you in the right direction. I'm not going to do that now. If you don't see your board here, then you'll have to go through a few steps to find out how to do that. There's a free book online called the Zynq Book Tutorial. Look that up online, and it'll also show you how to do that and give you some of the files you need to do that. Anyway, so here are the default settings that we have for this project. You can compare and contrast if you want. There's not much else to be seen here, and we're just going to click Finish, and it's going to build a default project for us. So we're using the canvas to build this project. It's a much easier way to build projects using the Zynq processor. So just go ahead and create a new block design. Click on that, and this will create a canvas area that we can start adding the Zynq processor to and some custom blocks. I like to name my block designs the same as the project, so this will be PS to PL interrupt. And I'm just going to go ahead and click OK. So we're leaning heavily on the tool chain in this design process. There's thousands of man-hours that Xilinx has put into creating these EDA tools for us to make things easier as far as creating designs. So go ahead and add a Zynq processor to the canvas. Right-click on the canvas, type in Zynq into the search box. That will pop up. Just double-click on that. It will add the Zynq processor to the canvas for us. And we want to run connection automation at this time. This only works because we're using a board support package for the Zybo board, and the toolchain has recognized that there are DDR. There's a DDR port for us that we can take advantage of, as well as another port. So we have DDR memory that will be configured automatically for us. Go ahead and just keep the default settings. Click OK. And we also have fixed I/O that has automatically gone out to a fixed I/O port. Now we have a lot of ports on the output we don't need, and the output is conventionally on the right side, so we can get rid of those. We can get rid of a lot of the things we don't need. So double click on the Zynq processor, and this will open up our Zynq processing system. A simple menu for choice selection of adding and removing peripherals in the Zynq processor. Now you'll see these green sections. These are the sections that are enabled. You'll see things like SD card, Ethernet, maybe I2C, SPI, and so on. And these are check marks next to it. We don't need those, so we don't need all of them for this project. We're only using the UART, so we're going to go ahead and disable most of them. So you can do that in the MIO configuration. Expand that and just go through these submenus and disable everything. For example, USB 1, we don't need that. Yeah, so just disable everything that we don't need. We are using the UART 1. This will be used to print out debug statements. Here we have some MIO GPIO we're not going to use. I'm going to disable that. And there's also a timer 0 in another submenu. Here's timer 0, and we're going to get rid of that also. Is there anything else? No. Okay, and we could click OK at this point. But I think we're going to go and enable the interrupts. We can do that also in this menu, so we might as well while we're here. So expand the interrupt section, and we want to enable the fabric interrupts. And there's a specific set of interrupts that we're enabling that you'll see here. So just select the options that you see here. We're not going to be dealing with specific interrupts from the PS to the PL, and we're not going to be dealing with interrupts targeted to specific processors. Now, this particular Zynq7000 processor on the Zybo board has 2 ARM processors on the inside, so we're not going to be dealing with targeting any specific one. We're going to select this option here. This gives us an interrupt port, you'll see, which will be generated shortly for a global interrupt controller. So once those are selected, go ahead and click OK. And it reconfigures the Zynq chip with the configuration that we're using. So that's your basic configuration. You can regenerate the layout, and this will always organize the routing in the canvas. No matter how disorganized it looks, it's guaranteed to make it a little bit more organized. Now notice the IRQ port on the left-hand side. This is an input, and there's specific numbers associated with it. So that is where we're going to be connecting our interrupt line to once we've generated our custom IP. Okay, so what we're going to do next is add a GPIO, AXI GPIO. So right-click on the canvas, click Add IP, type in the search box AXI GPIO. This will add an AXI GPIO block to our canvas. So double-click on that. See, it has added the IP. Next, go ahead and run connection automation. Click on the checkbox option to select all automation. You can kind of explore this and see where it's going. We want to select the GPIO option here. This tells the toolchain where the GPIO port is going to be interfaced, and we want to interface this to the LEDs on the board. You wouldn't have this option unless you had you select the Zybo board preset. That's what this tutorial is based on, so I hope you've done that. If you haven't, you'd have to manually configure them yourself. There's no reason to do that with the Digilant board support package for their Zybo board, so we have this automatic option here. With these settings, go ahead and click OK. Look at this AXI again here, AXI GPIO, and click OK. Okay, notice it's generated quite a bit of information. The design looks kind of cluttered. We can go ahead and click on Regenerate Layout. This reorganizes our block diagram. As you can see, the GPIO here is going out to the LEDs. Okay, we can double click on the block and see what's going on in the IP. This IP, the GPIO width, has been automatically configured to 4 as its output width, and these are all outputs. We're just going to keep the default settings here. We're not going to touch anything. We're not enabling the interrupt. We're not doing that. We'll be enabling the interrupt on our custom IP. So go ahead and click OK. We want to give this a name. I want to give this a name that we'll be able to tell when we go into our SDK what we're referring to. So this should be, we'll just call these LEDs. Or we're going to LED port. We can do that. LED port. Hit enter. Okay, so this is our basic block diagram here. Okay, for this next section, we're going to create custom IP. So at this point, we have an IRQ port on the Zynq7, but we don't have anything to drive it. That's fundamentally the purpose of this video, is to walk you through on how to create an AXI custom IP in the IP packager and have it drive the IRQ port on the Zynq processing system. So go ahead and click on. We go over to Tools, and we want to go to Create and Package New IP. This takes us to the Create and Package Manager. We can create a new IP for the Vivado catalog or for a new AXI for peripheral. Go ahead and click Next. We're going to create an AXI for peripheral device. This will automatically create the device itself, give a skeleton driver for it, which we'll be appending or using. So make sure that box is selected. Click Next. And we're going to name this PL to PS interrupt. Same name as our project and so on. Shouldn't really matter. This is just for the design for the PL to PS interrupt. So go ahead and click Next. This is the default option that it gives us. It gives us a S00 AXI as its name. The interface type will be light, and the mode will be slave. So it's going to be entirely driven by the AXI bus. And it's going to be a slave device. The data width is going to be 32 bits, so all the internal registers will be 32 bits, and we're going to have 4 registers on the inside. We're doing an interrupt project. This is going to be an interrupt device, so we need to enable the interrupt support. So go ahead and click on Enable Interrupt Support, and notice it's added another AXI port on the left side. The left side are inputs, and notice there's no outputs on the right side. So we're not going to have any outputs on this device. Um, this device will feature a timer internally, um, which will continually count down. When the timer reaches a certain value, it will trigger an interrupt and reset the count value and resume counting. That's what we're going to be doing. So go ahead and click Next here with these settings. Okay, what we want to do is we're going to edit the IP now. That's the first thing we want to do. Before we add it to any repository or do anything like that, we want to go ahead and edit the IP. There's some changes we need to make to the code itself before it functions as we want it to. Another thing we want to do is there's a few values in the IP code itself that will be auto-generated that we need to take note of. These will be important for enabling the interrupt and disabling it and acknowledging it and so on. So go ahead and click, make sure Edit IP is selected and click Finish. This is going to open up our new window here. This opens up another instance of Xilinx Vivado, and this is just for the IP that we're going to be using. So I don't want to do anything yet here, but what we want to do is go into the Sources window, click on the Sources and expand that button. Expand the PL to PS interrupt, and we want to click on this lower one here, which is our name, PL to PS interrupt, version 1.0 slave AXI interrupt instance, and the instance is an interrupt instance. There's a difference here between these two instances. This one is not the same as this one, so you want to make sure you're focused on the right one here. So double click that, and it will open up the code for us over here. So there's a lot of code that has been automatically generated. This is all for handling the interrupt and the slave AXI interface. And the code we're most interested in here is going to be the auto-generated code that Xilinx has provided us to help us get a handle on how the interrupt code works, and that's what we're going to be focusing on. We're not going to be modifying this too much. I want to keep this tutorial relatively simple. So if you scroll down, notice this is in VHDL. You're familiar with VHDL. This is the code that we are most interested in here. It's roughly around the line 400-ish. We have decoding, address decoding and reading registers. So notice the AXI addresses here is 4 down to 0. So what's happening is when we write to this register, we are going to be writing to the AXI device and the interrupt portion, and there's only three bits that are going to be examined here by this section of code. So you want to take note, the global interrupt enable is 0, 0, 0, right, of 4 down to 0. The interrupt enable is 0, 0, 1. The register interrupt status, it's going to be read-only, is 0, 1, 0. Our acknowledge is going to be 0, 1, 1, and we have a pending as well. The three most important ones are global interrupt enable, this one. Take note, 0, 0, 0. We have interrupt enable. This is different from global interrupt enable, which would be reading a 0, 0, 1. And we also have our acknowledge, which is 0, 1, 1. So take note of those values. be referring to them later. Yeah, I'll bring them up again once we get to the section where we need to really pay attention to that. What they've done for us here is they've given us AXI, or Xilinx has given us auto-generated code, and I'm looking for it now. And they've put a timer into this interrupt already. Here we have around line 467. If you're looking at this in Verilog, the line numbers are going to be different, but the idea is the same. I hope that you're familiar enough with VHDL. This makes sense to you. What you want to do is we have an interrupt counter here, and when the AXI slave is reset, 0 is asserted, the counter resets, so all the values in the counter go to 1, go to high. This checks it on the rising edge of the AXI clock. If the reset is asserted, reset the counter. Otherwise, if the reset is not asserted and the count does not equal 0, then we're going to subtract. So it's going to perform a subtraction on the interrupt counter. Okay. So we're going to be modifying this code, but before we do that, I think we want to expand the count register a little bit. I think the default code they give us is pretty small. So if you highlight that, it is going to tell you that it's only 4 bits wide. So 4 bits. Now our AXI clock is about 100 megahertz. Well, it is 100 megahertz. Such that when the slave AXI reset is asserted, and when it's asserted is low, when the AXI is reset, we are loading the counter with this hex value. X, there's an X there, and these are 32 bits expressed in hex. It's going to be 0, 5, F5, E100. And that is going to be 100 million. That's going to be 100 million in decimal. And why are we using 100 million for the loading the initial count is because the slave AXI clock is operating at 100 megahertz. So this will give us a count value counting down to 100 million, at which point we're going to reload the value in the counter again. It's going to subtract 100 million by 1 every time the clock occurs. And when it reaches 0, we're going to reload it with that value once again. So just to show you, decimal 100 million gives us this hex value. So you can use the programming calculator in Windows 10 or whatever version of Windows you're using to put the countdown value there. So I'm going to close that out. We've modified this code such that there's clearly no latch generation. The code before just had an else if the counter was equal to this, it would reset to some other value. So what we're saying here is on the rising edge of the slave AXI clock, if the reset is asserted, reset the counter, and otherwise, if the slave AXI reset is not asserted, here, this condition, if it's not asserted and the counter does not equal 0, we're just going to subtract. We're subtracting this counter value. We're taking the value in the counter, subtracting it by 1, and we're loading it back into the counter. This is just typecasting. VHDL is a strongly typed language, so you do need lots of typecasting going on here. We're typecasting it to an unsigned, where we could perform our arithmetic, and recasting it back to its original standard logic vector. Otherwise, in this line, if the counter is equal to 0 and the slave AXI reset is not asserted, remember, not asserted is high, asserted is low, right? We're going to load the counter again with a decimal value of 100 million. And under every other possible condition, we need to cover all possible conditions. This was not done in the code provided, so we've changed it to remove any doubt that there would be any doubt left that we haven't covered all possible conditions. So we're removing that, and we're pretty certain that we have covered all possible conditions because we have an else here. So under every other possible condition, we're just going to subtract. And those are the only modifications we made to this code, and that's all we've done here. So I'm going to stop the video for now. After we save, you want to save. Once you've made the modifications, save file. You want to go to let's see if we have to do anything else here. Don't think so. I do not think so. I don't think there's any values we have to write. There's nothing else we have to do. So at this point, we want to make sure we didn't make a mistake somewhere in the code. So go to the TCL console, clicking on the TCL tab, TCL console, TCL console, and you want to do check syntax. Type that command in and press enter. We want to make sure we didn't make a syntax error because sometimes you can repackage the IP and there will be a syntax error, and when you go to build the bitstream or run the implementation, it will then find that you've made a syntax error and notify you, in which case you have to go all the way back to the beginning, unpackage this, and re-edit the IP, find your error, and so on. It's frustrating. So this is so we've made 2 changes. That's all we've done. We've added this code here into the interrupt counter. And we've taken note over here. Oh, don't forget, remember, you do have to expand. You do have to expand this to standard logic vector 31 down to 0, so 32 bits wide. Otherwise, this won't work. And the third thing we did is we've taken note, go to around line 400 of these values here. These are important. So go ahead and I want to click Save File, allow it to save, and let's go back to our project summary, or we can go to our package IP. So click on the package IP tab over here. Let's go over to Review and Package, and before we do anything, we want to edit our package settings. So there's some changes that we can make that would going to help us find our IP in our main project, so this doesn't become very confusing. You want to make sure Create Archive of IP is selected here. It's not selected by default. You want to make sure the Add IP to the IP catalog of the current project is selected. You want to close the IP package window, and you want to delete the project after packaging. Now, this isn't going to delete all the changes you've made. You can always go back, right-click on the block in your block design and edit in. You can edit in the IP packager, and everything you have will come up again. So that's not detrimental. So it's okay. Delete the project after packaging. That's okay. So click OK here. There's a few other options here. We have identification. Just keep everything default. Here, I'm going to make it simple. Compatibility is Zynq. You can change the life cycle if you want. We're just going to keep everything default. Pre-production is okay. This doesn't affect the build or the bitstream. at least not for this tutorial. Keep everything else sort of default. Here, I'm not going to go into those. Here's some customization parameters. Go ahead. You can look at this if it helps. You can see that whether everything's the same or if there's minor differences. If you're using a different version of Vivado, it might be confusing, or it might be insightful. You might find some kind of differences between what I've done here and the later version of Vivado. You can see our ports. We have an IRQ port here. We have a slave AXI interrupt. We have this here. So just, yeah, keep everything the way it is. Notice the IRQ is a master. We're just going to keep that the way it is. Click on addressing in memory. You can click on that. And let's see what we have. We have 2 memory blocks, right? See, we have 2 under addressing in memory. Notice there's 2. So if you expand this, the name of the block is S00 AXI reg. That's going to be important later. And the name of this one is slave AXI interrupt register. These are 2 different things, 2 different AXI ports. Customization in GUI. I'm sure it's possible to get rid of this port. We're not really using the first slave port. We're just going to keep it there for now. And now we're just going to go ahead and review and package. So click on repackage. It's going to ask you if you want to close the project and click on yes. So the instance of Vivado has been closed, the other one for the IP packager, and you're left with our main project that we've had before. All right, for this next section, we're simply going to add the IP that we just created into our project. So go ahead and right-click on the canvas, click on Add IP. And if we remember what we named it, that's very important, PL to PS interrupt. So if you remember the name, you'll be able to find it in the search dialog here. And it has added it to our repository. If you didn't do that, you wouldn't have this in your repository. So go ahead and double click on it. And here is our AXI IP. That's all there is to it. It's put our block into our master block diagram. We're going to go ahead and run connection automation. So click on that and click on all automation. Notice we have 2 ports. We have the slave AXI interrupt and we have another AXI interrupt. Well, not interrupt, but another AXI port. So there's 2 ports here. Just keep these default settings, keep everything default, and click OK. And it has made a mess of our block diagram. There are connections everywhere. It's difficult to really look at, so we want to regenerate the layout. So right-click on the canvas and click on Regenerate Layout, and it has organized it up for us. What we can do at this point is draw a connection between the IRQ port and our IRQ F2P over here. And that's pretty simple. So hover your cursor over the IRQ port and just left click and draw it over here. See the check mark on the left tells you that you can simply connect it and let go. So that is going to generate an IRQ and interrupt into the Zynq processor. So we've connected that together. You click on Regenerate Layout again. At this point, the block diagram is mostly complete. The diagram is pretty much done. Go to the address editor and click on the address editor tab up here. Expand the processing system, and we're going to expand our addresses here. This is pretty important. We have our LED port, which has been memory mapped to this address, meaning that if you write to this address in SDK into the Zynq, it corresponds to writing to the slave AXI port. Likewise for our PL to PS interrupt here, and also this one here. The address is pretty important. Our PL to PS interrupt is this address here, this offset address. It's pretty important. So you want to pay special attention to that, because that's what we're going to be. That is going to be pretty worrying later. I have some issues with that. The tool chain has not automatically generated this for me when I've gone through these steps before. But there's a small workaround, which may not be uh, the formal official workaround for doing this, but I've gotten this to work. So go back here. So what we're going to do at this point is validate our design. Don't forget these steps. We want to validate our design. This may bring up some errors. I wouldn't be surprised. The first time it runs validation, it's not uncommon to get a couple errors for no particular reason. This appears to have been successful. Sometimes running the validation after getting some errors, they magically disappear, and I don't know why that is. We did not run into that issue here, so we have no errors. The next thing you need to do is, if you don't know how to do this already, go back to our sources and click on this little pyramid block representing our block design. We want to create a wrapper, so create an HDL wrapper. We don't have a wrapper for this yet, but we need one. And we're going to let Vivado manage the wrapper and auto update. We're not going to handle this ourselves. It's a lot of work that the toolchain does for us, and we're going to lean on the tools and allow it to do that for us. So click OK and let it run. It should happen fairly quickly. As you'll see, the wrapper is going to be generated in our sources. I'm not going to explore that. You can expand it. Our wrapper is here. You're welcome to go ahead and look at that. Now, anytime you come back to this block diagram and make any changes or edit anything, you're always going to need to go back and revalidate the design, and you're always going to need to go back and into the sources and right-click on our block design in these sources, and you're going to need to create a wrapper again. So otherwise, the changes may not be fully implemented, and you might be generating a bit stream for the wrong design. So at this point, we're going to go ahead and click Generate Bitstream, and we're going to use the default settings, launch selected synthesis or implementation run, so go ahead and click OK. And this is going to take a few minutes, so just go ahead and let it run. Here's Xilinx SDK. We want to export our hardware, include our bitstream. And we're going to go ahead and go to Launch SDK and let it open up the SDK project based on our hardware. It's going to import the hardware specification and a few other things, definitions and so on. So this is all you're going to have. This is all automatically generated here. It's given us driver files over here and a header file. These are empty. See the source file? All it does is import the header file, and it's empty. So you have to write your own functions for the driver. Also, the PL to PS interrupt header file. This is what it gives you. All we have are two macros that kind of look like functions. It's just a macro replacement for this definition, and it uses this Xilinx out32 function, which is defined in it's defined somewhere else. And there's also a test function as well. So we're not going to use any of this in our project, but note that's where it is. That's where it's located. Go ahead and click on New. Actually, let's go to repositories. So go ahead and add your repository for the project. It looks like it found it for here's our repository. If you don't know, if you can't find your repository, it should be under your projects folder, Xilinx projects, under IP repo. In Vivado, what we did when we created our IP was we created and packaged the IP in the IP repo, so it should find it there. Click on New, and then go find where the IP repo is and point it to the top level folder. And our top level folder in the repo was PL2PS interrupt. Click OK, and let's go ahead and create a new application project. We're not creating a board support package for this. As far as I know, this will be done mostly automatically. PL2PS interrupt. Give it a project name. Create a new BSP. Make sure it's in C, and keep everything else the same. Here, click on Next, and we're just going to create an empty application, so this has no files in it. And then click on Finish. Okay, look at all the building that's being done by the compiler. There's a lot of make going on here. Let it do its thing. This may take a few moments. Okay, when it's done, as you can see, there's 3 folders total. 2 extra ones have been created. We have our BSP and we have our PL2PS interrupt. I'm going to minimize these 2 folders for now and our PL2PS interrupt. This is our application folder. We have a source folder. We have a bunch of includes. You'll notice an include for our PL2PS interrupt over here. What I'm going to do is go to the top level, and we're going to create 3 files. We're going to create a source file for our main application. Call it main.c. You can call it whatever you want. We are also going to create a new file for our driver. Let's create a header file. ps driver.h, right? .h extension is a header file. Finish, and we also need a file for the C file, which will have our functions. So go ahead and create new, create a source file, call it pl2ps driver.c. Okay. In our main, we need tmain return 0, file save all. It's our driver. Our PL2PS driver should be importing the header file, so you're going to want to include driver.h. Whoops. Let's go back here. Okay, and here is where we're going to be writing all our functions. We're going to create a bunch of functions in here for our interrupt. We're going to put void instances of those functions here, and we're going to create a structure and so on. So this is how you set up the files for this particular project, and that's pretty much how that works. So I'm going to go ahead and import the code that I've written already. So going to our driver file, I'm importing the code that I've written for this already. We're including our header file, and then we've created functions for our driver to disable the interrupt, enable it, global, enable interrupt, and acknowledge the interrupt. In our header file, see, it was we have this code here. Let's not save as, let's just save it. Save all. When you click save all, with the default settings, it should auto build the project. If you start getting the strange errors that you've seen previously in the video, there's a file issue. Don't struggle with it. Just just go ahead and create your own driver files and put them under the top level folder here, and the toolchain should be able to find them. Again, if you know how to point the files to the correct places, go ahead and do that yourself. I'm not an expert in that, and it's always has given me problems in the past. Save all, and as far as the main, go ahead and click File, Save all. And it looks like we're okay. Let me go ahead and run this again. Give it one last check to verify it works. And there's no issues, so you don't have an issue when you do this. And that's pretty much it. But what I've done is I've been able to get this to work. So your basic file structure is going to be based on a project we create here, new project application. Here's our main.c folder. We have our includes. We are including all the files and the drivers that we need to run our application. We have xparameters.h. These are the parameter files for hardware descriptions. Really, these are referring to addresses, memory space. You will need that. Let's go back to main here. GPIO is the driver file for the AXI GPIO. This is the header file for the global interrupt controller. This is for Zynq's exceptions, which is needed for certain functions in setting up the global interrupt controller. Over here we have status. This allows us to use printf and just prints the status out of our UART. And of course we have our own driver file here, PL2PS interrupt. Next we have defines, definitions that we can use between our main file here and our xparameters file over here. So everything on the right hand side you will find in the xparameters.h file here. For example, the interrupt controller device ID, we need to know what that is because we're going to be setting that up later. So if I hit Control F, Control V, you can find that. This is the definition for the peripheral for the SCU GIC global interrupt controller, and it's 0. And we use that later momentarily. There's other device IDs which you'll need. Our PL2PS base address is here. It's a 0x43C10000. Now you won't find this in the xparameters.h file, but you will find it if we go back into Vivado. If you were to open your block design, and if you were to go to the, let me close all this out, go to the address editor, it's right here, PL2PS interrupt, and it is a slave AXI interrupt, and the interrupt register is here. Now, if you don't do this, you will not be able to access the interrupt. It won't be triggered. You won't be able to configure it. So it's very important that you do refer to that address. Let's see. Next, we have we have a base address for our LEDs, our GPIO port. You can find that also in the X parameters. You can go to find, and that's set up automatically for us. The base address is 0x41200000. So Next, we have structure declarations. These two structures you can find, well, they are defined in our XGPIO and our XSCGIC, or Global Interrupt Controller. Um, so you can simply use these structures without having to fill in anything. This XPL to PS, we have to make this structure ourselves, and we write that in our own driver. So I'll go over there into our driver, and looks like I've defined it in the header file. So in the header file, this is the structure you're going to need to add to your own custom, into the custom header file. It's this. So go ahead and place that in the structure definition in the header file. And that allows you to use this to create an instance of this structure, which we need. We have our prototype definitions here. This is just for the handler. So you'll need a handler. This handles the interrupt. In the handler, you disable the interrupt, and we've written a driver function in our own driver. You need to acknowledge the interrupt, and then after disabling the interrupt, acknowledging it, you need to enable it again. And we put printf statements in there to demonstrate that it's functioning, and we can verify it works over the UART. Then we have a main function. This is the main body function here. We have, we're going to initialize the GPIO output for the LEDs. That's all this does. This function here sets the direction. For outputs, the argument's going to be low. If you don't know what the function does, you can always click on it, open the declaration, and this will take you right to the description here. As you can see, setting the data direction, it takes an instance pointer of the XGPIO, channel number, and a mask, a direction mask. And it writes to that memory space certain values. This is not intuitive. You'd actually have to go straight all the way down to the hardware to really verify what it's really doing. I'm not going to do that, but you can simply use this driver function to set that. As far as configuring our custom pointer to the XPL to PS instance, we have a base address, which is the base address given through memory mapping. PL to PS base address, and which said defined here as 0x43C1000. So that's important. So fill in these structure fields with this information. The XPL to PS instance is ready. Is going to this is hex. All ones. There's 8 ones. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 8 ones. So this tells it that it is ready. This is standardized by Xilinx. You'll find it elsewhere in other code for telling or getting the structure to an is ready state, and it's going to be defined here. Is present is 1 and is dual is 0. We have a printf statement to verify it is working. After initializing our custom PL to PS interrupt structure, we want to initialize the global interrupt controller. This is almost a cut and paste job from other code I've seen. This code initializes the driver well, this is the global interrupt controller. So you have a pointer to an interrupt controller config, and the interrupt controller config pointer takes the output of this function, which is just looking up the configuration of the global interrupt controller based on its device ID. Next, we have a status is going to be returned from initializing all this information. We have the instance pointer, we have the configuration, XSCU GIC config pointer here, and the config CPU base address we're passing here. You're welcome to explore what these functions do, highlight. You can open declaration if you want to do that. Next, we're enabling both interrupts. and then following enabling both interrupts. We're going to write these functions, how to do that. Following doing that, we have a, we're going to be enabling the exception handler register. If the exception, if there's any exception during this setup, it's gonna trigger a fault, and we won't be able to run the code. But what we will see is that a fault occurred, and we'll know it has something to do with a status return from somewhere in our code. Okay, so after enabling these exceptions, what we have here is we're connecting our custom PL to PS interrupt to the global interrupt controller and our handler. So you have an instance pointer. So this is the address of the instance pointer. We have the interrupt controller, PL to PS interrupt ID. Then we have our function handler name. This is over here. This is our function handler name, right? This is the handler for the interrupt. And then we have a pointer. Well, we're passing the address of our structure also into the global interrupt controller connect. So this connects everything together. All the interrupts are connected together using this function with this code. And then finally, once we've done that, we want to go ahead and enable our PL to PS interrupt again. We enable the interrupt and we enable the global enable interrupt. So there's two things you want to do here. And then finally, we enable our global interrupt controller with this function and these arguments here. And then lastly, I just have a small function where setting a delay value, initializing LEDs. These are the LEDs on the Zybo board, and we're going to sit in this while loop and count up to 10 million. We're going to toggle the LED values, and then we're going to write those LED values to our LEDs on the Zybo board, and that's it. If ever we get to here, which we won't, it'll return 0. So that's all that's doing. An overview of our PL to PS driver.h code. What we have is these are header guards. You're not going to get too much in here, except you won't see this yet until you have to fill this in yourself. We have them if defined C++. We want to use this extern C. This is a bracket here, and the other bracket is down here. So if this is defined, if C++ is defined anywhere, we're bracketing this code. So put that in there. This is in other header files as well for other drivers like the GPIO. You'll see this as well. You'll have to explore that. We've included these 3 header files. We have the types. Zylinx types allows us to use different types, status, and Zylinx IO, which allows us to use Zylinx IO function here. This is not an explicitly defined function. It's defining wherever we see this anywhere in the code, just replace it with this, and that's how this the standard driver file works. You're also going to want to put this in your code as well. I've done it because other header files have done it for the project, so I'm doing it as well, and I'm trying to make everything as close to what the other Zylinx header files have done. The structure we need to create. I'm going to type def structure u int ptr u integer pointer is a base address. We have this holds the base address into the structure. We have an isReady field. Then we have an interrupt present field as an integer and isDual field. And we're type defing. Making a type definition of the structure. It's going to be xpl to ps right here. So this allows us to use this structure, create a new one, and assign values to it. This was auto-generated by the code. This was auto-generated by the code. And Xilinx also generated a PL to PS interrupt self-test, which we can run. I'm not going to do that here. And we want to define functions. We have a we want to define a PL to PS interrupt. We want to disable the interrupt. We want to enable the interrupt. We have a global enable interrupt, and we have an acknowledge interrupt. And these are going to be defined in our C file over here. It's our C file. I'm going to close some of these out here. I'm going to go ahead and open the C file. We can simply go to that now. Okay, so we're going to go to our C file here. These are the function definitions. I've had to redo this because I did run into some trouble earlier with, what was it? It was files not saving. Their files not pointing to the right places. So that there's something on this there's something in this Eclipse IDE where there's a setting I haven't done properly or something. But this is the way I've structured the code here. It's flat. If you know how to point libraries to the right places and not confuse the tools, then of course you're more than welcome. Put these in the appropriate files you want to. Put the header information in the file you want to. But I've flattened it out to make it as simple as possible. So here we are back in our driver. We want to disable the interrupt, and we declare a register. We have an interrupt enable register offset is going to be 0x04, as I've explained earlier. And the register mask sets it low, right? We're simply writing. We are writing that value. We're using this function. This function was defined in PL2PS in the driver here. And we're just writing to the base address and the offset. And we're taking the value we read and we're ANDing it with the inversion of the mask. So the mask that we pass in here is going to be just 1. So that means when we invert that, all the bits will be high except the least significant bit, which will be low. So what this does is sets that 1 bit low, and that disables the interrupt. That's how that works. To enable it, we're doing pretty much the same thing as we did above. We're using the same offset, so we're writing to the same base register and offset, and we'll be writing a 1 there, and this will be the lowest significant bit, and we're keeping all the other values except the lowest significant bit we'll pass in. We'll show you that in main through the mask, and that just makes sure it's high. That's all it does. For the global interrupt enable, we have our offset is 0, so take note of that. And we also use an OR mask to enable the global interrupt. If you want to disable global interrupts, you can certainly write your own global interrupt disable function and use an inversion of the mask and AND it. So it's a read, modify, write operation. So that's our global interrupt enable. And our final function here is a PL to PS interrupt acknowledge interrupt. So we're acknowledging the interrupt, and that clears the interrupt. It lets the global interrupt controller know. Or actually, it lets our device know that we've acknowledged the interrupt by writing to that address space. And we're doing a read, modify, write operation, and we're ORing it with the mask. So that is that's the anatomy of the driver. Your code should look like this. I don't see any reason to type it out. Pause the video, go through it piece by piece, and that's probably easier for you to do that on your own rather than me typing it out line by line. So once again, this is the PL to PS driver. I'll just scroll down here. And this next is going to be your PL to PS driver. This is the .c file, right? This is the .c file. So you're more than welcome to pause the video and kind of get this working. And make sure your files are over here under the project application. If you accidentally open this by mistake, and if you accidentally refresh these files, what you can do is simply go into, actually right-click on the folder and click on Clean. Click on that, and when you've clicked Clean, go to Build a project, and it will make sure the references are referring to the same places there. So going back to our main, I don't know if there's much reason at this point to write each piece of code out piece by piece. You can see the code here for yourself. So that's what I would recommend is just copy this code. What I do want to point out again, this is very important, you may not have the same base addresses for these devices, so just copying these definitions won't work. It's not going to work, so you have to refer to xparameters.h when you use these definitions up here. And for this base address of your custom IP for the interrupt, you have to go refer to the address of the slave AXI interrupt register, which is here. It might be different for you. It might build differently. I don't know. But you definitely do need all these definitions. You need the interrupt C device ID. So all these definitions here on the left, the PL2PS device ID, all this is in the main body code in this file, right? And everything over here, the XPAR PS7, XPAR PL2PS interrupt, well, except for this, but all of these definitions are going to be in xparameters.h. So you have to go to this file xparameters.h, and you have to find what those are. And for things like base address, refer to the base address here for the definitions they give you. For the LED port, right? Not hard. For the LED port base address here, right? This is auto-generated by the toolchain. Right, see what we're doing? X LED port base address. See, that's all we're doing. And then we're creating our own definition to refer to on the left side. So you have both base addresses and you have device IDs. So both are important to get this code working. Here's the device ID for the XPAR LED port device ID. The same with our PL2PS. We have a device ID. We have a base address. Our interrupt controller has its own device ID here, so we don't need the base address per se. What we do need when we use the interrupt for our PL2PS, we need this XPAR fabric PL2PS interrupt 0IRQ interrupt. Now, if you named it something else, it's not going to have the same name. So how are you going to know what it is? Well, go into X parameters. I'm going to find this here. You're going to see definitions for a fabric interrupts connected to the SU global interrupt controller. And you're going to see something like this. So the interrupt here is going to be number 61. How do we know that's right? Well, let's go back into Vivado. And if I open the block design, here's our Zynq processor. I'm going to double click on that. I'm going to wait for it to open and click on interrupts. Remember, we did here, we have fabric interrupts. You could find this in the data sheet if you want to, but we have our interrupts are going to be between 61 and 68 and 84 and 91, right? And this enables our 16-bit shared interrupt port. Okay, so we know that's right. Let me go ahead and close that out. That's how you know you're okay on those definitions. So that's pretty much it. I'm going to go ahead and run the code now, and I can show you how it works. I put additional print statements in here, so we can see how it's initialized. And this is going to trigger every 1 second, and that's it. Okay, so what I'm going to do at this point is go ahead and program the FPGA and run the code. If you don't know how to do that, you should probably go to some material that's a little more introductory, because I would guess you're probably lost by this point. Programming the FPGA is very basic, so go ahead and program the FPGA. Configuring the FPGA at this point. Yeah, if you don't know how to do that, I don't know what to say. Just if you've made it this far and you don't know how to program the FPGA, well, congratulations. That's quite a feat. I'm going to go ahead and run. Actually, we're going to run as debug. So debug as launch on the debug platform. So while this is launching, what I'm going to do is open up my MOBA Xterm. This is a free application. Go ahead. Whoops, why is this not open? And I'm going to go ahead and click on run. So clicking run, there's your interrupt handler. Let me pause this for a minute here. Let me pause this. So I've paused the application. So as you can see, we have entered the main. We've initialized our PL to PS interrupt. We've gone through counts 1 through 5. We have an interrupt ready to go. And every time the interrupt is triggered, we're running through printf statements in the interrupt handler. Now you can do whatever you want in the interrupt handler. It's completely up to you. I've just put printf statements. I think at this point it should be pretty clear the functionality of how this is all working and functioning together. If you've gotten this far, I'm sure you can take it much farther. So we'll just keep this running. Let's go ahead and reset the terminal. There it goes. About every second we have the interrupt, and that's from that hex value that was taken from 100 million from hex. The hex value, I believe, if you've done that value correctly, I believe it was 0x5F5E100. My memory is serving me. If you entered a larger value, this will take longer. If you entered a shorter value, this interrupt will be firing quite rapidly. It may not have any opportunity to do anything else on the board. LEDs are toggling simultaneously on the board, and you should be able to see that. I've included a video of that functioning with the LED. So if you see your LEDs frozen, it means your interrupt is by the time it really completes, it's being triggered again, and that value of the counter in the VHDL code is too small, and you're welcome to experiment with that. And so forth. But anyway, so yeah, so that's the overall functionality of how to get an interrupt working. I think what I'll do is I will add the code somewhere. I'll attach the code, but the most important thing really is knowing how to modify it using the X parameters file. And once you have it working, once you have the code working, it's not much of a logical leap to modify it and get it to do what you want, or use it to learn. You can certainly use this as a learning platform to increase your knowledge. I found this quite challenging because at least at the time of this video, there weren't many good resources on how to do this on the internet. Nothing for just a simple interrupt straight from a PL device into the PS. So that's all for now. Thank you for watching, and I'll leave it here.